Today I'll be talking about multiscale modeling and analysis of multiphase alloys, and I will be focusing on homogenization-based multiscale modeling coupled with crystal plasticity constitutive model. I would like first to acknowledge my co-authors, so Igor and Miguel, which are PhD students, and Daniel, which is a postdoctoral student that did his PhD in Swansea, and you can see immediately the link, and then he did a postdoctoral at Porto University. So this is the outline of the presentation. I will start by addressing the main motivation and the objectives of the work. I will then focus on the formulation of higher order multiscale models and their finite element implementation. Then I will move to material constitutive modeling and will address crystal plasticity constitutive modeling within the context of multiscale models. Several examples combining the two previous ingredients will be then presented, and finally I will finalize with some concluding remarks. So we have witnessed over the last years and also in many presentations during this conference that there is an increasing interest in the multiscale mechanics of materials. And the underlying idea is always to predict the macroscopic response based on the underlying microstructure. And this is very important when the material behavior at the microscale is very heterogeneous. Typical examples are polycrystalline materials, porous and cracked media, composites, biological materials, so the list never ends really. If we now focus our attention on a particular class of materials, so polycrystalline materials, significant efforts have been made to develop new alloys with improved mechanical properties. And normally what is done is we blend multiple crystalline phases in a complex microstructure, and we try to obtain an improved behavior. So there is normally a trade-off between strength and ductility for the majority of steels. Nevertheless, we have seen over the last years advanced high-strength steels emerging, and we've got some examples there of TWIP and TRIP materials that can actually incorporate the two extremes of the table. So they have very high tensile strengths and also very high elongations. More recently, with the advent of blending 5 or more constituents, we also have high entropy alloys, which have really unprecedented properties and seem to be a very promising avenue for the future in terms of material development and also in terms of giving properties that are not seen till today. The design space for materials is then, of course, vastly expanded when we can really mix different constituents of interest. And of course, computational methods have, from my point of view, have had an important role and will definitely continue to have a very important role in accelerating the development of new materials tailored for each specific application. Therefore, in order to enable the analysis and design of metallic polycrystalline materials, I'll address today two ingredients of multiscale modeling that we've been working on. So the first one is the influence of strain gradients on the behavior of metallic structures, and they are very important for structures that are subjected to deformations with high curvatures. For example, self-deployable structures are currently using elastic hinges, and this kind of hinge undergoes high curvatures during the folding process, requiring very carefully attention during the design. Strain gradient effects are also very important for the prediction of the behavior of materials in micro and nano systems. And in fact, the community has dedicated a considerable attention to this subject, and we've had in this Congress in particular several sessions dedicated to this. The second ingredient is the coupling between crystal plasticity and martensitic transformation. The coupling of these two phenomena is actually very important. There are transformation-induced plasticity materials, and this is probably one of the most adopted strategies for alloy design. The reason for that is because it's relatively inexpensive, and they can really improve the strength to ductility ratio, which is one of the avenues that we need to pursue in order to have lighter structures and more resistant structures. And although exceptional performances have been reached over the last 2 decades, renewed interest has actually emerged with the development of the third generation of advanced high-strength steels, where this coupling of martensitic transformation and crystal plasticity has gained momentum again. From an algorithmic perspective, this class of problems is actually known to be very challenging, and I will give particular attention to their efficient numerical simulation. So, before actually addressing the development of higher order multiscale models, I would like to recognize that strain gradients can appear mainly for two reasons, and I'll try to explain a little bit better. So, one of them is because of the geometry of the loading itself or the boundary conditions, and that's what I have on my left-hand side of the slide. So for instance, in bending, the strain is large at the surface, but it's almost zero at the axis of bending. When we have an indenter, the strain is very large beneath the indenter, but is almost zero far from it. So we have strain gradients that emerge due to either the geometry of loading or of the boundary conditions, but we also can have strain gradients which emerge from the microstructure of the material itself. For instance, when deforming crystals containing hard, non-deforming particles, local strain gradients between the inclusions actually develop, and when, for instance, we have the mismatch of slip at the boundaries of these different crystalline phases, we also have strain gradients there. So bear with me in the next slide. So in order to capture these strain gradients with the continuous formulation, the common practice is really to enrich the displacement field with higher order terms. So just to explain for the ones which are not familiarized with this, so if we have, for instance, an RV in the initial configuration, and if we enforce just the first gradient, what we normally are able to get is really either tension or compression or shear. Nevertheless, if we actually enforce both the first gradient and the second gradient of the displacements, we can enrich the number of deformation modes that we have, and we can get extensional, curvature, trapezoidal, and twist modes. So when second gradient is considered, the infinitesimal volume can actually undergo additional deformation modes. So in the context of FE square, there have been, I would basically say that there are two approaches for multiscale modeling. The first one, which I'll label standard second-order homogenization, where pioneering work has been done by Kuznetsova in 2002, and later on by Lusher and Blanco, all following slightly different techniques and assumptions. And the normal course of action in the analysis is basically we prescribe to a macroscopic cause point the first deformation gradient and the gradient of the deformation gradient to a microstructural volume element. Every microstructural constituent is actually modeled with a classical continuum, and the RV problem is formulated in terms of standard boundary conditions. And from the solution of that microstructural boundary value problem, we actually can compute the macroscopic higher order stresses and also the tangents that we need to run a fully coupled FE square simulation. We have also derived this and implemented it, but today I will address what I'll call a fully second-order homogenization. And fully, for me, basically means that I have a second-order problem at both scales. So I will enforce on the microstructural representative volume element both the first and second gradient displacement on the RVE. A second-order RVE problem is formulated and solved, and then from that solution we will obtain an higher order solution for the first Piola-Kirchhoff stress tensors and the higher order stress tensors, and we are also able to derive the tangents that we require in order to have the system completely linearized, and we can solve it with the Newton-Raphson method. So this is the setting. So I'll now dedicate some time to explain the formulation of this fully second-order homogenization. And in order to derive this formulation, we have employed the method of multiscale virtual power, which has been proposed relatively recently, and we have basically to postulate two operations. The first one is the kinematic insertion, and this is basically we have to express how the microdisplacement is a function of the macroscopic quantities, and the kinematical homogenization, which is basically how the microscale kinematical quantities are, in this case, averaged in some sense to produce the corresponding macroscopic quantities. All the steps that are required are then defined by the method, and the constraints which define the kinematic admissibility are really the result of compatibilization between the kinematic insertion and the kinematic homogenization definitions, and the compatibility is actually ensured by the constraints which are actually both of them in force at the RV level. So since we are using a second order continuum at two scales, then we will need to discretize the problem with C1 continuum elements. There are different approaches in the literature to do this. C1 elements, we have the discontinuous Galerkin method, and we also have mixed finite element method, mixed finite element, sorry. The first two actually require the use of a large number of integration points, and since we are interested in solving a coupled problem, if we want to have an efficient computational framework, we should minimize the number of Gauss points, and that is the reason why we've selected mixed elements, both in 2D and 3D. These elements are actually stable. We can use it with reduced integration, which is another advantage because we sample it in less number of Gauss points, but we have an expense, which is the number of degrees of freedom of the problem actually increases. But in terms of a trade-off, this is probably a better solution. Therefore, in addition to the displacement gradient field, we also have, in addition to the displacement field, we have a deformation gradient field as an unknown of the problem, and the compatibility between both of them is actually enforced by Lagrange multipliers. So we have here the macro weak equilibrium equation, where we also have the higher order stress and the higher order strain, as we should in a second order problem. We are using a mixed formulation where the compatibility between the two deformation gradients is enforced by a Lagrange multiplier, and then we discretize the problem and finally consistently linearize it in order to use the Newton-Raphson method. And with this, we have the macroscopic problem, equilibrium problem, completely defined. Since we have adopted a mixed formulation for the macroscale problem, the transition of scales now needs to be modified, and we need to define an expression for the microscopic relaxed deformation gradient that is independent, of course, of the microscale displacement field. The kinematic homogenization operations actually are exactly the same, and then by enforcing the second kinematic insertion with the kinematic homogenization, the second constraint becomes a boundary condition applied to the relaxed deformation gradient of the fluctuations. We will again employ the Lagrange multiplier method to enforce the microscale kinematic and constraints, and we'll use actually three Lagrange multipliers: L, which is a second order tensor and enforces the first constraint; M, which is a third order tensor, which enforces the second constraint; and finally lambda, which enforces the continuity of the deformation gradients. The principle of multiscale virtual power is used to provide the physical link between the two scales, and it basically states that the power that we produce at the macro scale should be equal to the homogenized microscale virtual work. The strong form of the microequilibrium problem can be obtained by setting some of the multipliers to 0, and we can also obtain the higher order stresses from this procedure. The advantage of using the Lagrange multiplier method is that each multiplier actually assumes a very important physical meaning, being related to the first order stresses and the second order stresses. So actually, although we're using the Lagrange multiplier, at the end, both Lagrange multipliers have the very physical meaning. We can also obtain the microscale equilibrium equation by setting the variation of the deformation gradient and its gradient to 0. And if we enforce the two constraints that I've mentioned previously in the stiffness matrix, we finally get a system of linear equations that we solve with the finite element method, and it is possible also to derive the consistent tangent matrix which link the micro and the macro problem. So the problem is actually fully coupled, consistently linearized. In order to illustrate the differences between these formulations, I'll use a very classical problem which has been published many times and presented many times. This is the boundary shear layer, which basically it's a material layer with a height h, and in the other two directions it has an infinite length. And due to that infinite length in the other two directions, the finite element model can assume just a plane strain stripped of elements with periodicity enforced on the degrees of freedom of both sides, and the results actually only change on the direction x2. So what I'll try to show is what results do we gain, or what results we obtain when we use a first order, a standard second order, and a fully second-order formulation. So to do this, I'll go to the most basic example that I can imagine. So I have an RV composed by a soft matrix with hard inclusions, both linear elastic. So it's really the simplest case with 3 different sizes. Since I'll show first the first-order formulation, I'm discretizing this with bilinear quadratic elements. And what I'll show in this slide, you can see on the left-hand side the macro scale geometry of the strip. And on the right-hand side, you can see the 3 RV sizes that I'm considering. Of course, I've scaled 2 of them in order to make them the same size and to be easy to appreciate the difference on the results. So as we deform at the macro scale and the micro scale, we can see that locally we have slightly different results. But when we plot the profile of the deformation gradient, what you see there is basically a straight line, which means that for every different size of RVE, we get always the same solution. So basically this means that as long as the RV size is large enough to capture the heterogeneities of the material, when we upscale that to the macro scale, we don't get that information passed on. So now, in order to clarify the difference between the 2 second-order formulations, I will use this scheme, which varies on the x-axis the RV size and on the y-axis the size of the constituents. So, and we'll analyze the 2 effects separately. Let's start with the effect of the RV size. Let me also mention that all the RVs have been generated with the same volume fraction of 20% of hard inclusions on the RVs. And although I'll only show one example of each, we've actually did several realizations of all of them, and the results are more or less the same, so the differences are very small. So let us analyze then first the impact of the RV size. And if you look carefully, the 3 RVs are exactly the same. I've just scaled the size. I haven't changed anything. The microstructure is exactly the same, just the scale, just the size has been scaled. So now I have got 3 layers. So from the left-hand side to the right-hand side, I'm actually increasing the size of the RVE. I've again scaled the sizes to be the same. They are not the same, they are just scaled for visualization purposes. And I'll show, as the deformation evolves, what happens for 3 elements within the stripe, how the deformation evolves. So what we can see is the first case is actually almost the first order formulation, so we don't really have quadratic displacements. It's almost a linear deformation, and as we increase the size of the RVE, you can see especially on the bottom size RV that the quadratic displacement becomes quite visible. If we again plot that on the macro scale and we see the plot of the deformation gradient, this is with the larger size of the RVE. If I decrease it slightly, and again, we recover almost the first order formulation. So we can see that this formulation, which has already been around for some time, can really capture the size of the RV very well. And that influence is really seen when we upscale the information from the micro to the macro size. If we now fix the RV size and just change the size of the constituents, and we run the analysis again, so it's exactly the same approach. So we have the vertical stripe, we have the 3 RVs, and we have the size of the constituents changing from the left to right. So left is the largest size, and on the right is the smaller size, and we'll show the deformation, the profile of deformation. And what we can see is that although locally at the micro scale, we can see that the fields actually change, they are not really the same. When we actually plot the results at the macro scale for the profile of the deformation gradient, I'm plotting the 3 of them, we see that the results are almost the same for the 3 sizes of the constituents. So what we are actually realizing is that although we can capture the size of the size of the RV, the size of the constituents doesn't seem to be captured by this formulation. If we then go to the second order formulation, also at the micro scale, and we're using now the middling elastic constitutive model with the same 3 sizes, and I'll run exactly the same simulation, what we'll see, and that will become slightly clearer on this picture, is that for the smaller constituent size, we actually get almost a linear deformation. and for the largest constituent size, we get a more quadratic variation. So then, if we upscale this information again, and I go back to the same slide, we can clearly see that if we change the size of the constituents at the micro scale, at the macro scale, that response is actually upscaled, and it's affected on our problem. So the conclusion is really depending on the class of problems that we want to solve and the type of size effects that we want to capture, we can select different types of multiscale formulations. This fully second-order formulation would be appropriate for the cases where we are really interested in capturing both size effects at the material scale and eventually gradients at the macro scale. And with this, I've finalized the first part of my talk, and then I'll move on to the second topic, which is crystal plasticity constitutive model. And here, the coupling again, I'll mention again that the coupling between crystal plasticity and Martin-City transformation is very important for many materials. And from a modeling perspective, these materials are actually quite challenging because we have a complex interplay between a variety of physical phenomena at the crystal lattice scale. And I think multiscale models can really help to clarify what is happening there. So the model itself, which I'll show very briefly, uses for the crystallographic slip the well-established theory of slip, which has physical roots in the dislocation mechanics of materials. And for the Martin-City transformation, we will use the phenomenological theory of Martin-City crystallography. And this theory, although it has been extended many times since its inception, it has, I would say, stood the test of time, and it's still used for a large number of constitutive models. So this theory predicts for a given combination of input and product lattices a set of possible transformation systems. We have here for a single transformation system defined by normal and tangential directions that the deformation gradient can naturally be defined, and we can see that the magnitude of the shear and normal components can actually be quite large, and therefore finite strains need to be used. And if at a given material point, if we consider all the potential concurrent transformation systems, the overall deformation or transformation, gradient of transformation, can be described by introducing a volume fraction for Martin-Site transform along each system, and this is also referred in the literature as a Martin-Site variant. Patel and Cohen observed that mechanical loadings have an influence on the transformation starting temperature, and they proposed a very simple transformation criteria, which was at that time limited to small strains and uniaxial stresses, which states that the transformation occurs when the work done between the applied stresses and the transformation displacements reaches a critical barrier. And that was the criterion that they developed, which we have extended to large strains. So, following standard practices in crystal plasticity modeling, we can actually decompose the deformation gradient in different components. We have an elastic deformation gradient, a plastic deformation gradient, and also a transformation deformation gradient. And this actually implies the existence of two intermediate and stress configurations on top of the reference and current configuration. And one is the plastic slip, and the other one is the Martin-Site transformation. And then we can actually formulate a model very similar to crystal plasticity. So if for crystal structures we say that plastic activity occurs when the component of the stress parallel to that specific slip direction reaches a critical value, we can actually say in a similar manner that a Martin-Site transformation occurs when a specific transformation direction stress parallel to that direction also reaches a critical value. For slip plasticity, we have a plastic law. For Martin-City transformation, we can also define a transformation rule. For slip plasticity, we have an yield function, which defines the onset of yielding, and for Martin-Site transformation, we can also define a transformation function. So this enables us to have a fully set of equations to solve that we will integrate with a very conventional elastic predictor plastic corrector scheme. So we do an elastic trial, we do a consistency check, and if we don't satisfy both conditions, we have to do a multi-vector return mapping. We have discretized the plastic flow rule with the exponential map to preserve plastic incompressibility, and we have adopted rate-dependent regularization, and this actually has the advantage that can actually the rate is used for both the plastic part and also the transformation part, and by changing appropriately the viscosity and the strain rate, we can actually model both strain rate and rate-dependent problems. After discretizing the problem and writing it down, we actually arrive at a system of 3 equations. The first one is a function of the elastic deformation gradient. The second one of the hardening of the material. We will have 12 equations if we are talking about an FCC slip, and 24 if it's a BCC slip. And finally, one additional equation, which can take up to 24 equations for the Martin-Cytic transformation. One thing that we've realized is that if all slip systems follow the same hardening curve, which actually is commonly assumed for FCC and BCC, it is actually possible to create coplanarity groups among the slip systems, and we can reduce this number of equations only to 4 equations. And this actually accelerates significantly the Newton-Raphson procedure at the Gauss point because the number of equations is actually quite large. So we have a system of equations where we have a fully coupled slip plasticity and Martin-Cytic transformation. They both evolve simultaneously. We have linearized it to obtain a consistent tangent modulus, and we have quadratic convergence. And this is particularly important, particularly in the context of fully coupled analysis, since we really want to move in time and fast. And if we have an incremental cut at the Gauss point in one RVE, that will force the microstructural boundary value problem to cut, which will then force the macroscopic problem to cut. So after linearizing it and running some problems, we realized that doing the full linearization wasn't enough to run this class of problems. So then we added a few techniques. The first one, which is well known, is called sub-incremental strategy, which basically sub-increments the deformation gradient at the Gauss point that is having more difficulty in converge, and we can do this several times. We've used it up to 8 times, but you can use it with more times. And we basically cut the incremental deformation gradient, and instead of doing it for the whole problem, we just do it locally for the Gauss point of interest. Another thing that we've used, we have started the Newton-Raphson procedure with viscoplastic properties, but followed an approach proposed initially by Professor Stein that was mentioned some days ago, where we actually changed the exponent and the viscosity parameters, and then actually after we converge to that, we divide it by 2 and so on and so forth. If we actually do a logarithmic discretization of the viscoplastic properties, we observe that the convergence improved significantly. So we were actually able to converge a lot better when using this logarithmic discretization. And finally, we also implemented a strategy proposed by Knežević and Koch in order to eliminate the rate dependence of the viscoplastic law. So what they basically suggest is that we substitute the viscosity by the local strain rate, and that makes the problem a little bit easier to converge. Of course, if we do that, additional terms emerge on the linearization that we need to take into account. Just to show the power and the importance of doing this, I'll just use one single Gauss point with a deformation gradient that can range from pure shear to simple shear with the material parameters that I have there. And on the next slide, I'll show, so this is the convergence ball. And what we can see on the top is the strain rate. As the strain rate approaches rate-independent solution, the red space basically shows you that we were not able to converge. So, but even for rate-dependent problems, really rate-dependent problems, the colors show that we are only able to converge in the beginning, and this gray color is just the elastic domain, and after that we can converge relatively well with very, very small increments, but as soon as we increase the increment size, the problem fails to converge. And here I'm showing just the results of the Newton-Raphson method coupled with the sub-incrementation strategy that I mentioned, the first one. And you can see straight away that if we don't allow it to sub-increment, we almost don't converge. So the timestamp at the Gauss point level is really very large. When we use the 3 techniques combined and we go to the more difficult problem, what we see is that we can converge almost for all cases without any problem. So this is really, for us, was actually quite impressive. And the message is that sometimes only consistent linearization might not be enough. And these techniques, when combined, really improve the problem. And the speedups that we get by doing this can be up to 1,000 times. Sometimes we don't even get convergence. And by using this, we can converge in really a reasonable amount of time, which is quite impressive from my point of view, at least. So now I'll show some examples where I'll couple the two things. So the higher order multiscale approach with the crystal plasticity, with the transformation that I've shown. So the first example, it's a beam, bending of a beam, of course, and of course the second order effects actually emerge due to the geometry of loading. So we will enforce 180 degrees on the beam. The beam is going to be modeled with 250 elements, 861 nodes, and the rotation is going to be enforced in 30 increments. At the micro scale, we are using an RV with 500 grains, and the properties are from an austenitic stainless steel. So this is fully coupled. On the left-hand side, we have the geometry of the beam after being deformed, and we have basically selected one Gauss point where we'll actually monitor the evolution of the fields that we want. So that Gauss point is actually in the center of the specimen. So in this slide, on the left-hand side, I actually have that RV. On the top, we have the second order formulation. On the bottom, I have the first order formulation. And on the right-hand side, I have the macro scale deformation. And I'll play the slide where you'll be able to see the two scales deforming at the same time. So in this column, I will plot the effective Cauchy stress, and now on this column, I'll actually plot the volume fraction of martensite. And I'll play it now, and you'll see that as we deform, the first order formulation has a lot of rotation, but very small deformation. And when we look at the contours of the stresses in the RV with the second order formulation, we see a straight line. I'll play it again just and what we actually seeing is that the neutral axis is actually going from bottom to up, and with the second order formulation we can actually capture that evolution. Another thing that is interesting to note is that the volume fraction of martensite that transforms is significantly higher with the second order formulation. On the first order formulation we almost don't have any transformation, and with the second order we have a significant amount of transformation in this problem. If we look at the homogenized stresses versus the rotation angle, first I have the first order formulation, and then I'll increase the size of the RV once and twice. And what we can see is that the Cauchy stresses, which are the ones on the left-hand side, actually decrease. And they decrease because since we have positive and negative stresses, when we do the volumetric averaging, we actually have lower Cauchy stresses, but then the second order stresses actually increase. Now I'll show my last example, which is a three-dimensional example, fully coupled, where I've used an apparatus, which is a kind of a shear specimen, where we can actually rotate the apparatus with the same specimen, which is this one. In the literature, it is known as the butterfly specimen, and we can then test different loading directions. This is the dream for every material model. So different in-plane directions can be tested and then experimentally validated. I'll basically show one or two cases of this, and the points that we'll analyze is one point in the center of the specimen and the other one on the boundary of the specimen. Let's start with so the microstructure of the material is again discretized with an RV with 250 grains. It's again an austenitic stainless steel, and we'll do the same strategy that we shown before. So I'll have my macro scale geometry where I have the equivalent strain and a measure of the second order strain on the right hand side, and then on the left hand side I've got the micro scale RVE. On the left I'll show the transformation of martensite, the volume transformation of martensite, and on the right I'll show the effective Cauchy stress. So as the loading is applied, we can observe that the results change with each formulation, and we are actually analyzing the central point. So even though the magnitude of the second order gradient is large in the center, since in this case the problem is dominated by the first one, we really don't see a significant difference between the two formulations. So the first order formulation, when the first gradient is really the dominant one, is the one that will give actually the right solution. Well, both give the right solutions. Nevertheless, now let us move, and if you look at the curves, there are all of them are actually one on top of the others. Now, if you go to the point which is on the boundary, which is not in the center of the specimen, what we actually can see, and I'll play this, so it's exactly the same thing. So we have on the right-hand side the macro scale specimen with the equivalent strain and also the a norm of the second order strain. I have the effective Cauchy stress on the right and the transformed volume of martensite on the left. If we now play the movie, what you can see is that the deformation on that point there, the second order mode can actually capture the opening of the element and it gets thinner on the other direction. If we see at the amount of martensite as transformed, this example also is a lot more significant than the first order formulation. So the message here is that we cannot just look at the first order gradient, but also at the second order gradient, since both of them are actually very important on determining the response of the overall problem. When we look now at the response, we can see that in that point, the second order gradient actually increases significantly. We can see that as we decrease the size of the RV, and the Cauchy stress is decreased also quite significantly because we are on the boundary. So in many problems that we have, when we have an homogeneous stress state, second order formulations might not be able to capture more information than the first order formulation. Nevertheless, if the deformation is not homogeneous, and if we have a specimen which has a geometry which is a little bit more complex, many times, and what we've realized is that the second order formulations start capturing deformation behaviors that we cannot see only with the first order formulation. So I'm coming to an end. To finalize, I'll say that a fully second order multiscale framework has been developed and implemented. We have enriched deformation modes at the RV level, and we can capture both the RV size and the size of the constituents in the scale transition. The crystal plasticity constitutive model has been developed. We can have the two phenomena completely coupled and evolve simultaneously. The problem has been consistently linearized both at the local level and global level, and I've mentioned that it's extremely important to employ additional algorithmic strategies to improve the performance. Some of them have been mentioned, so all of them actually have a significant impact in our simulations. The numerical results show that second and first order response actually converge as the RV size decreases, as they should. And depending on the RV and the size of the constituents, we can actually observe significant differences on the homogenized response. These differences can be alleviated when the deformation is dominated by first order modes, but in the general case, we can really see significant differences. And to finalize, I would probably say that it's necessary to account for strain gradients in order to quantitatively capture the behavior of a multi-phase microstructure. Thank you for your attention.